Welcome to Mogojastro. Today I am going to discuss one important topic, that is why potential is a scalar quantity, and if and this question is obviously come in your mind and you get so many answers in the net and so many answers in the YouTube, but I am going to show you why this potential exactly is a scalar quantity. That means so before you start, you know that scalar quantity means that only has the magnitude, that doesn't have any direction. If there is a direction, then that means if we want to discuss about any quantity and that is dependent upon the direction, then we can say that it is a vector quantity, and vector quantity is a cross product and scalar quantity is a dot product. So you know these things. Okay, so that means we can say that V is equal to E dot ds, where E is the electric field, which is a vector quantity, and ds displays a vector quantity, but the potential is a scalar quantity. Now why it is dot product, that you should know. Okay, and one thing, that is, if 2 points are there and if you want to reach from point A to point B in we can say we can reach point A to point B in different way. So the way must be like this, the way must be like this, the way must be like this. That means if the initial point and final point is a path independent, then we can say that that this is a path independent quantity. That means we have to prove that the potential is a path independent quantity. So now, to establish that, you should take one positive charge q over here. Okay, this is one q positive charge. So there are so many radial field lines. So for positive charge, the field lines are away from the, you can say that the field lines are away from the charge. That is the field lines are like this, like this, like this. Okay, the field lines are like this. Now if you want to displace a charge, that means if you say that a charge q naught charge is displaced, a q naught charge is displaced from point A to point B. So this is the magnetic, the electric field lines are away from the charge, and it is available up to the infinite. Okay, like this. There are the radial. These are the radial electric field lines. Okay, these all are the radial electric field lines. Now you want to, so if the position of this charge is, this is the charge q, this is the charge q naught, and if the distance of this charge from that q is r, you can say that r is the position vector, and this is, and you can say that ra is the distance between the positive charge q and the a, that is the ra. And if you say that the distance between this positive charge and this point b is rb, then you can say that that to, so this is the q charge is along the electric field line, that is that the electric field lines are radially outward. Okay, now what happened, that is the, as there is a positive q charge and q naught is a test charge, so there is some force which is which the q naught is experienced, and the force fr when it is in r at position r, then the f become 1 by 4 pi epsilon naught q naught by r square, that is from Coulomb's law. Okay, this is the equation 1. Okay, now so we want to displace the charge from point A to point B. That means we have to do some work against the electric field, or with the electric field. That is the another issue, that is depending upon the displacement and the electric field. If they are opposite to each other, then we should do some work done against the electric field, and if they are in the same direction, then we have to do the work towards the electric field. Okay, now so to displace, so the work done, what is the work done? So we have to find work done to to displace the charge Q naught from A to B. So if the work done is denoted by A to B, we can say, then we can say that work done is equal to, we know W is equal to F dot ds. So we can say that is the here, that as it is denoted by the distance is denoted by r, so we can say that integration of f dot fr dot dr, and the integration limit is, it is the ra, that is the from ra to rb. Now we can integrate it. Okay, so if you put the value of fr, so it is ra to rb, and the fr is the 1 by 4 pi epsilon naught if it is in the air, and if it is in the medium, then it is f 1 by 4 pi epsilon m q naught by r square into dr. Now what are the constant term? That is the q naught of the constant term, and the 4 pi epsilon naught is the constant term. But r is not a constant term, because this force which is experienced by q to q naught is not the constant, because if ra is when this is the distance, then it is ra. When this is the distance, then it is rb. So as it is a function of r, that is the force is a function of r, because if r is increased, then force is decreased. So if we want to displace the charge from point A to B, then work done should be variable, because the force is variable. Okay, so what? So the integration is ra to rb 1 by r square dr. Now you know the integration of, that is the q naught by 4 pi epsilon naught, that is the, this is nothing but integration of ra to rb, that is the r to the power minus 2 dr, and if you integrate it, then it become q naught by 4 pi epsilon naught, that is the minus of 1 by rb minus of, that is the what is the integration of this? The integration of this is become minus 1 by r dr. Okay, 1 by r, that is, you can say that we can write it, the integration 1 by minus 1 by r. Okay, the integration limit is ra to rb. Now go to this line, so 1 minus 1 by rb minus of minus 1 by ra. So if the final result is, that is the final result is the q naught by 4 pi epsilon naught, that is the 1 by ra minus 1 by rb. Now what is the fundamental thing? That is, fundamental thing is that there is the work done to displace the charge from A to B, that is path independent. Why path independent? You can see, look, this thing, this is a constant, q naught 4 pi epsilon, all of the constant, but the what is the, what we can change, that is the ra and rb, that is, this part is not constant, this is variable. That means only the work done is dependent only the initial position and the final position. That's why it is path independent, and as it is path independent, that's why potential is a scalar quantity. Now another thing that is, that maybe arise in your mind, that is, if we can erase this thing now. So you can say that, sir, this is the radial field, and the charge which is displaced from A to B, that is a straight line. That's why you can say it. Now we are taking another thing, that is, we are taking the charge, that is a positive q, this is the positive charge, and we can draw the radial field line like this. So a radial field line may be drawn like this. Okay, so that means these are the radial field lines which you can draw. That is, the electric field lines are coming out from this charge. Now we have to displace the charge. Okay, so we have to displace the charge in a curvilinear way. Then we can determine that what is the path independency of the displace the charge. Now we have to displace the charge from this position. You can say that the charge can be displaced from, this is your A position, A, and this is your B position. Okay, so you have to displace the charge in this way. That is in the curvilinear motion. Now, so this is your position A, and this is your charge which is at position R. So you can say that this is your charge Q naught, which is at this position. So this is the distance between these two is RA, and the distance between two is RB, and the distance between these two is, you can take the another color. So this is the distance is the RR. Okay. Now, so electric field lines are radially outward. So these are the electric field lines. Now, when the charge Q is here, what is the direction? You can take the charge here also. That means you can draw one field lines like this, which is passing through the charge. Then it is easier to get the point. So this is another electric field lines. There are so many field lines. Now, so what is the direction of the force? So direction of the force is in this direction, because the electric field is in this direction. So the direction of the force is also in this direction. Okay. Now, so if the force is in this direction, so force, here we can magnify it. So force is in this direction. Displacement is like this, in this direction. That is the point B. This is the point A. Now, electric field is also in this direction. That is if you draw the electric field also in this direction. So that is the same direction. That is the direction of field and the direction of the electric field are same. Okay. Now, if it makes an angle theta, because the displacement vector, this is the dr, that is the displacement vector is in this direction. The displacement vector is along A to B, that means in this direction is the displacement vector dr. So what is the, if it is electric field, then so what is the component of electric field in this direction? That is along the direction of the displacement, that is the E cos theta. Now you can calculate the work done. So work done for A to B. So it is become integration of RA to RB, because the position vector are RA to B. So what is the F? What is the component of force also? Force is also F cos theta, because the force is acting in the direction and the charge is displaced in this direction. That means the component of F is also F cos theta. Is it? Okay. Now, so the electric field is in the direction of the force, and the displacement are in the same direction. If we take the component of force is F cos theta. So it is the F cos theta into dl. That is the dl is the displacement. dl is the displacement vector which is acting along this. So it become, so we can write RA to RB. F is the 1 by 4 pi epsilon naught Q naught by R square into cos theta into dl. Okay. Now, what is cos theta dl? What is cos? You can say that dl cos theta. What is dl cos theta? So now, if force is in this direction, then the dl should be also in this direction. But you see that the charge is displaced from A to B in this direction. That means dl also a direction towards it, and this is also dl cos theta. So what is dl cos theta? Dl cos theta is nothing but that is the dr. Is it? So dl cos theta is nothing but the dr. Now you can say that it is now integrated RA to RB 1 by 4 pi epsilon naught q naught by r square, and and for dl cos theta we can say that dr. Now if we integrate it, then you can get q naught by 4 pi epsilon naught into 1 by RA minus 1 by RB. The integration is same as the previous page. So this is the work done for moving a charge in a curvilinear way. And it means that for previously, if the means in the previous page you see that to displace the charge for A to B in a straight line, the work done is this. And for same electric field, if you displace the charge from A to B in a curvilinear way or any other way, then also the work done is 1, that is same, that is the q naught by 4 pi epsilon naught, that is 1 by RA minus RB. That means that here also the work done is the path independent, that is it is only dependent upon the initial and final point of the position. That's why we can say that potential is a scalar quantity, and this is the exact explanation why electric potential is a scalar quantity. And as you can say that A to B, you can say it is a potential difference. If the A point is infinite, then that is the initial position is at initial position the potential is 0, so it become WB, that means the potential. If we are considering A to B, A and B are the finite point, then it becomes the potential difference. So whatever it is, potential or potential difference, the thing is same, that is the potential or potential difference, both are the scalar quantity. This is the exact physical representation of the potential as a scalar quantity. So see you in the next video with some interesting topic. Good night.